We have introduced the overall framework of oil recovery, and now we begin with the first recovery stage, primary recovery. As we go through the next slides, please keep in mind that each recovery stage reflects the condition of the reservoir and the amount of energy still available inside it. Primary recovery refers to producing oil using the natural energy present in the reservoir, or with limited mechanical assistance such as artificial lift. Natural depletion means we simply produce the oil until reservoir pressure declines to the point where further production becomes uneconomic. The main limitation of primary recovery is that it cannot recover all the oil in place, because it depends heavily on natural reservoir drive. This is why understanding the reservoir drive mechanism is so important. The drive mechanism is like a gift from nature. It determines how much energy the reservoir has and how strongly fluids will move toward the wellbore during the early life of the field. This table summarizes the main reservoir drive mechanisms and their typical recovery ranges. For example, in a solution gas drive reservoir, the energy comes from gas that was dissolved in the oil and then expands as pressure declines. Recovery may be around 5 to 30%. In a gas cap drive reservoir, the gas cap and evolved gas provide pressure support, so recovery is often somewhat better. In a water drive reservoir, energy comes from aquifer expansion, and recovery can be significantly higher. Gravity drainage can also contribute, particularly when density differences allow oil, gas, and water to segregate naturally. This table is important because it shows that not all reservoirs behave in the same way. The recovery factor during primary recovery depends strongly on the natural energy mechanism. In a solution gas drive reservoir, the main energy source is the gas originally dissolved in the oil. At the beginning, the reservoir may appear to be entirely liquid, but because pressure is high, gaseous hydrocarbons are dissolved in that liquid. As production begins and pressure falls below the bubble point, gas comes out of solution. This exhaled gas expands and helps drive the remaining oil. Over time, some of the free gas may migrate upward and form a secondary gas cap. The key physics here is gas expansion. However, solution gas drive reservoirs often experience relatively rapid pressure decline, so recovery can be limited if no pressure support is added later. In a gas cap drive reservoir, a gas cap already exists at the top of the reservoir. As oil is produced and the reservoir depletes, the gas cap expands. Because gas is highly compressible, it can provide a strong source of energy and help maintain reservoir pressure longer than in a pure solution gas drive reservoir. This expanding gas cap pushes downward on the oil column and supports production. In general, gas cap drive can produce better recovery than simple solution gas drive, although much depends on reservoir geometry, vertical communication, and operational strategy. In a water-drive reservoir, the main source of energy is an aquifer connected to the oil-bearing formation. As oil is produced, the aquifer expands slightly and pushes water into the reservoir, helping to maintain pressure and displace hydrocarbons toward the wells. This is often a very favorable drive mechanism, especially if the aquifer is large and well connected. The slide also shows two common types: bottom water drive and edge water drive. In bottom water drive, water pushes upward from below. In edge water drive, water advances laterally from the side. Water drive can give relatively high recovery, but it may also lead to water production problems if water breakthrough occurs early. Gravity drainage is driven by density differences among gas, oil, and water. Because gas is lighter, it tends to move upward. Water is heavier and tends to move downward. Oil occupies an intermediate position. This natural segregation can assist recovery, especially in thick reservoirs with good vertical permeability and structural relief. However, gravity drainage alone is usually not a very strong mechanism. In practice, it often works together with other drive mechanisms. Still, in certain reservoirs, especially fractured or steeply dipping formations, gravity can play a very important role. When natural reservoir pressure is no longer sufficient to lift fluids to the surface, we introduce artificial lift. Artificial lift refers to mechanical systems that help bring well fluids to the surface or reduce bottom hole flowing pressure so the well can continue producing more effectively. The slide lists 4 major artificial lift systems: electric submersible pumps, gas lift, hydraulic pumps, and beam pumps. These systems do not create oil in the reservoir, but they help us recover it more efficiently by improving wellbore lifting performance. An electric submersible pump, or ESP, is a downhole centrifugal pump powered by an electric motor. The pump and motor are placed below the fluid level in the well, and the motor drives the pump to force fluids upward through the tubing to the surface. ESP systems are especially useful for high-rate wells. Their performance can be adjusted by changing the number of pump stages or the motor horsepower. The main advantage of ESPs is their ability to handle large fluid volumes efficiently. However, they require electrical power and can be sensitive to gas handling in downhole conditions. Gas lift is another very common artificial lift method. In this system, high-pressure gas is injected into the well through the annulus and enters the tubing through gas lift valves placed at selected depths. Once the gas mixes with the liquid in the tubing, it reduces the average fluid density in the tubing column. Because the fluid column becomes lighter, the pressure required to lift it to the surface decreases. Gas lift is flexible and useful in many field conditions, especially offshore or in fields where gas is readily available. It can also tolerate sand and certain wellbore challenges better than some pump systems. A hydraulic pump system uses high-pressure power fluid instead of gas to lift produced fluids. There are two main types, piston pumps and jet pumps. In piston systems, the power fluid drives a downhole motor connected to a positive displacement pump. In jet pumps, a Venturi effect is used to mix the power fluid and produced fluids. One advantage of hydraulic pumping is operational flexibility. Jet pumps, in particular, can handle wider production ranges and may be less sensitive to solids than some other systems. However, hydraulic systems require surface fluid circulation and proper fluid handling, which can add complexity. The beam pump, often called the nodding donkey in the field, is one of the most recognizable artificial lift systems. It uses a surface pumping unit to reciprocate a rod string, which drives a downhole positive displacement pump placed below the fluid level. Beam pumps are widely used, especially in onshore oil fields. They are robust, well understood, and suitable for many low to moderate production rate wells. They are a classic example of simple but effective petroleum engineering.